Now let's look at how to count significant figures. All non-zero digits are significant. So this 1.5 measurement has two significant figures. Interior zeros are always significant. This counts, so 1.05 has three significant figures. And this is a sticking point for many students. Trailing zeros after a decimal point are significant. What is a trailing zero? It is a zero that comes after the last non-zero digit. So it is always zeros at the end of a number. So this zero counts because there's a decimal point. Leading zeros are all of the zeros that come before the first non-zero digit. So these are all leading zeros. They are never significant. This zero counts because it's between two non-zero digits, and this zero counts because it's a trailing zero and there's a decimal point in the value. A way to avoid the problem of leading zeros is to express the number in scientific notation. 1.050 times 10 to the minus 3. We have 4 sig figs here, 4 sig figs here, ends all confusion. Now, this is a subset of Rule 3 right here, the trailing zero. Zeros at the end of a number without a written decimal point are ambiguous and should be avoided. So if there's not a decimal point, this zero doesn't count. 150 only has two significant figures. So to express that without any confusion, 1.5 times 10 to the 2. If this value actually does have three significant figures, then 1.50 times 10 to the 2. So let's look at this in a little bit more detail. Let's look at these three different representations. And again, in math land, all four values would be the same. But in chemistry land, we have to really be careful about the precision of our instrument, and our numbers are used to reflect that. So this only has one sig fig. This has no decimal point, so this trailing zero does not count. This value, this 10, however, has two sig figs. The only difference is the presence of this decimal point, and that's extremely important in chemistry when you're dealing with trailing zeros. It doesn't matter in math or your calculator, but it matters here. This would have three sig figs. All the zeros would count. These are trailing zeros, and they all count because there's a decimal point. And this here would have four sig figs. These zeros count because there's a decimal point. The zeros count because there's a decimal. Trailing zeros count because there's a decimal. This trailing zero does not count because there is no decimal point expressly written. And then let's review the difference between measurement and exact numbers again. Exact numbers are considered to have an unlimited number of significant figures. There's no uncertainty. And a number whose value is known with complete certainty is considered to be exact, and as we went over earlier, from counting individual objects and then also from definitions. For example, 1 centimeter is exactly equal to 0.01 meter. Okay, so pause the slide and see if you can, or actually pause the voice lecture and determine how many sig figs are in each of these values, and then when you're done, turn it back on and we'll check your answers. So this has two sig figs. The leading zeros don't count. This has four sig figs because the trailing zeros count. The trailing zero counts because there's a decimal point, and the interior zero counts. This is all non-zero digits. They always count. This has four sig figs. The power of 10 does not count toward significant digits. So this only has three sig figs. This right here is a definition. So this has unlimited number of significant figures. And then this is ambiguous. It really only has 1 according to our rules. Okay, let's look at this next exercise here. Determine the number of significant figures, the expected range of precision, and indicate the last significant figure. So let's just do this example first, so you know what to do. Okay, so first let's identify the last significant figure. There are trailing zeros here, zeros at the end of the number, and there's no decimal point expressly written. Therefore, this is our last sig fig. There are only 2 sig figs total, and our last sig fig is going to be our estimated. So our range of precision is going to be plus or minus whatever this place value is. This is the thousandths place value, so it's plus or minus 1,000. So that means that this measurement can be anywhere between 13,000 to 14,000. It's not very accurate, but perhaps it's a technique that's used to measure people in a crowd or something like that. But remember, the range of precision is always plus or minus 1, whatever the place value of that last sig fig is. So go ahead and pause the voice lecture and see if you can get through the rest of these. Okay, so let's look at our answer. We did this one together. Here, this is our last significant figure. There are only 2 sig figs because the leading zeros don't count, and it's plus or minus 1 of the 10,000th place. So minus 1 here would be 0.0011, and plus 1 would be 0.0013, plus or minus 1 of this last. Okay, this has 3 sig figs. This expressly written decimal point means this 0 counts, the trailing 0, and it's plus or minus 1 of the last place value. So 1, and the last place value is the ones place. So 120 minus 1 is 119, and 120 plus 1 is 121. Let's look at this one. This has 3 sig figs. The leading zeros do not count, and this trailing 0 counts because there's a decimal point. So our precision is going to be plus or minus 0.00001. If I subtract that, I get 0.00119, and if I add that, I get 0.00121. Let's look at this. There are 4 significant figures. These zeros count, they're trailing zeros, and there's an expressly written decimal point. Our range of, I don't know if I said this, there are 4 sig figs, and our range of precision is going to be plus or minus 0.01. Our last significant digit is in the hundredths place. So if I subtract 0.01, I get 11.99, and if I add 0.01, I get 12.01. So our measurement is somewhere between here. Let's look at this. This also has 4 significant figures. Our interior 0 counts, 1, 2, 3, 4. Plus or minus 1 is our range of precision because our last significant figure is in the ones place. So if I subtract 1, I get 1,200. If I add 1, I get 1,202. Remember, our exponent does not count towards our significant figure. So this has 3. This trailing 0 counts because there's an expressly written decimal point. So our last significant digit is in this place. Now remember, it's not going to be the hundredths place because this is in scientific notation. The value of this number really has the decimal point 3 places over to the right. 1, 2, 3, which means our actual number is 1,200. So if we look at this, (1.20) times 10 to the 3. That's where our last sig fig is. I write this out in standard notation. That is where my last allowable digit is, this first 0 here. This number actually is 1,200, but according to measurements, this is where my estimated digit is. So it's going to be plus or minus 10. So it goes from 1,190, which would be this value minus 10, to 1,210, which is this value plus 10. So that's where this came from. And then here, this only has 4 significant figures. This is our last significant figure. These trailing zeros do not count because there's not an expressly written decimal point. So this is in our thousandths place, so our precision is plus or minus 1,000. If I subtract 1,000 from this value, I get 1,200,000, and if I add 1,000, I get 1,202,000.